Let's look at this problem. How many positive 3-digit integers have a remainder of 2 when divided by 6, a remainder of 5 when divided by 9, and a remainder of 7 when divided by 11? Interesting. This is a number theory problem. By reading this problem, I can think of a couple of methods to solve it. One method will be fairly general, but a little bit tedious. But it's good to solve almost all such kind of problems. So I will introduce that first. And the second approach may have to take advantage of some specifics in this problem. And we will discuss that later on. Okay, let's start with the first method. Let's call that method 1. In this method, we will use equations to interpret these conditions specified for this integer. And then we will find the solutions by analyzing these equations. Okay, let's start it. Let's set this integer n. Right? Since it's a 3-digit integer, it got to be between 100 and 999. And at the same time, since it has a remainder of 2 when divided by 6, I can write it this way. N equals 6x plus 2, where x is an integer. Or we can also write this integer in this way. 9y plus 5. That's from this second condition. A remainder of 5 when divided by 9. Or we can write it in a third way by this third condition. A remainder of 7 when divided by 11. So n can be written as 11z plus 7. Good. And all these variables n, x, y, or z are integers. But x, y, and z are not free variables. They got to take values within certain bounds. Let's bound these 3 variables first. For x, since 6x plus 2 is n, and n is, let's write it this way, since n is greater than or equal to 100, therefore 6x is greater than or equal to 98. X is greater than or equal to 16 something. Given that this x only takes integer values, x is greater than or equal to 17. And what is the upper bound? We get the upper bound by restricting this value by 999. Then 6x is less than 997. X is less than or equal to 166 dot something. Therefore, the upper bound for x is 166. Now let's look at y. We'll use the same approach to bound this variable y. 9y plus 5 is greater than or equal to 100, right? We don't have to solve these equations very rigorously because we can make a guess. In this scenario, y can take a value of 10, right? In that case, this gives 90. And then plus 5, that's 95, right? Then y got to be greater than 10. Therefore, the lower bound for y is 11. How about the upper bound? The upper bound is from 9y plus 5 is less than or equal to 999. A good starting point for y would be the value of 111, right? 9 times 111 gives you 999, but that is greater than 999. Therefore, the upper bound for y is 110. Similarly, we can get the bound for z. So 11z plus 7 is greater than or equal to 100. Then we can try the value of 9. 11 times 9, that gives you 99. Plus 7, that is right above 100. Beautiful. So the lower bound for z is 9. Then let's look at the upper bound. 11z plus 7 is less than or equal to 999. We can try the value of 90. If z equals 90, look at this. 11 times 90, that gives you 990. And the plus 7, that is right below the bound of 999, right? Z can't take any value greater than 90. Therefore, 90 is our upper bound for z. Good. With this bound in mind, we can start analyzing these functions. All right, let's clean up some space. And you may wonder, why do you want to check the bounds first? That's a very good question. The reason I check the bounds first is because of this. Look at these functions. We have 3 functions, but we got 4 variables: n, x, y, and z, right? So there's no regular way to solve 4 variables out of 3 equations. Therefore, we got to do some interesting analysis of these equations so as to list all the possible solutions. All right, let's start it. First, let's eliminate this variable n, because it's less interesting. We want to check the variables of x, y, and z, because their coefficients, these coefficients, gives some interesting information. So let's try that. The first equation would be 6x plus 2 equals 9y plus 5. And the second equation is 9y plus 5 equals 11z plus z. So basically, this equation is from the top 2 equations by eliminating n. And the second equation is from the bottom 2 equations by eliminating n. Some students may wonder, why do you choose this way? Why don't you combine the first and the third equation? Why don't you do that? The short answer is, I don't think this is unique. You can probably try that as well. But let me give you a reason why do I do this. First reason is, this is the most natural way to look at things, right? The first and second, and then the second and third. But this is not a very good or mathematical reasoning. A good mathematical reasoning is actually this. Look at this equation. So if you look at this equation, when we move this 2 to the right-hand side, or in other words, if I minus 2 on both sides of this equation, I will get this. I will get 6x equals 9y plus 3. Do you see anything interesting? I think so, right? Because all the coefficients are multiples of 3. Therefore, you can simplify this equation. How about the second equation? The second equation is also interesting because we want to write it in this way. We want to write it in this way. 9y minus 2 equals 11z. Then some students may wonder again, why do you choose to rewrite it this way? So let me tell you why. Again, I don't think this is unique. Probably if you put this 2 to the right hand side as 9y equals 11z plus 2, and then you can probably solve this problem as well. But the reason I choose to do it this way is because in the next step, I would divide 11 on both sides. So let me write it out. I'll interpret it as I write it. So again, the first equation gives we divide 3 on both sides. So the first equation gives 2x equals 3y plus 1. Good. And let's look at the second equation. I want to write the second equation in this way. Z equals 9y minus 2 divided by 11, right? So let's continue to explain why I choose to write it this way. Why do I choose to solve z in terms of y, not vice versa? The reason is I want to divide both sides by a large number, as large as possible. And at the same time, I want to keep both sides an integer, right? You don't want to divide by an arbitrary large number. Therefore, you either divide both sides by 9 or divide both sides by 11. So 11 is a larger number. When this divisor is as large as possible, when we consider all the possible solutions, this quantity can reduce in a faster way. But again, this is not a very rigorous reasoning. This is just like intuition in my mind when I solve these equations. That's one reason. The second reason is I want to divide both sides by a prime number, if possible at all. Why do I choose a prime number? Because the benefits of a prime number is that it can either be, this numerator can either be divisible by this divisor, 11, or not divisible at all. There are no partial cancellations. If you divide both sides by 9, then there could be some partial cancellations, right? Because you can cancel a 3 from the top and the bottom. But again, such choices are simply from some of my experience while I solve similar number theory problems. It doesn't mean these reasoning are valid or the only good way to solve this problem. All students are encouraged to try the other way. For example, to solve y in terms of z, and then see if you can get a better solution. These intuitions are just bare in the deep of my mind through the years of solving such a number theory problems. They may be right or may not be right. It's just experience. So I share it just in case you may find that helpful. Okay, let's continue rewrite the right-hand side. We don't want to leave it here. The reason is this. You look at this 9, this coefficients of y, this 9, right? This 9 is a fairly large quantity, and that is fairly close to this 11. So in order to make the following analysis easier, I want to reduce this problem slightly. Again, this is also an intuition. It may or may not be the better way to handle this problem. Anyway, let's continue. So I want to write 9y as 11y minus 2y, and then 2y, and then minus 2, divided by 11. Now, let's take this y out, because we have 11y here, right? So we can write it as y minus, look at here, we have a coefficient of minus 2 and a minus 2. Therefore, we can factor it out. This will help reduce this problem further. Therefore, that equals y minus 2 times y plus 1 divided by 11. Good. So I'll call the first equation, equation 1. The second equation, equation 2. And we will get all of the possible solutions by analyzing these two equations. Okay. Let's get some clean space. Now, let's look at the first equation, equation 1. What can we get from equation 1? We noticed that on the left-hand side, we have 2x, which is obviously an even number. Therefore, the right-hand side should also be an even number. In order for 3y plus 1 a even number, if that is even. And that implies 3y got to be odd. And that implies y got to be odd. Good. This piece of information will simplify the following analysis. Now, let's look at the second equation. Equation 2. Since in equation 2, the left-hand side is the variable z, which is an integer. Therefore, the right-hand side got to be an integer as well. For the right-hand side to be an integer, right-hand side to be an integer or a natural number, right? Z is a natural number, it's a positive integer. This implies y plus 1 divided by 11. This got to be a positive integer. Good. We will start from here. And let's look at this y. In order for this to be a positive integer, y plus 1, this y plus 1, got to be a multiple of 11. Or in the other way, x plus 1 got to be divisible by 11. Alright, but are all 11 multiples good in this scenario? Probably not. Check this condition out. Y got to be an odd. So the easiest choice for this case is y plus 1 equals 11, right? When that equals 11, y equals 10. This contradicts that condition, right? Therefore, we know this y plus 1 got to be even multiples of 11. It cannot be odd multiples of 11, right? We can check 33 again. If y plus 1 is 33, an odd multiple of 11, this gives y equals 32. Again, that's an even number. It's wrong. Therefore, y plus 1 is even multiples of 11. That's our conclusion. All right, let's clean up some space. Since y plus 1 has to be even multiple of 11, so the choices are like this. Y plus 1 equals 22, or 44, 4 times 11, or 66, 6 times 11, or 88, 8 times 11, or 110, 10 times 11, and so on and so forth. I'll mark these possible choices in this way. So since this is 2 times 11, I'll call it 2 times. This is 4 times, I'll call that 4. And this is 6 times, I'll call that 6. This is 8 times, I call that 8, and so on and so forth. Right, the next would be 12. All right, so don't get worried about this. We are almost there. Why? Because look at this. There is a bound for y. So that's why we choose to get the bounds for all variables, all these variables first. So obviously we can't go to the infinite. We'll stop somewhere. All right, let's try it one by one. When y plus 1 equals 22, y equals 21. That implies z equals what? Z would equal, here, equation 2. Z would equal 21 minus 2 times, since this is 2 times, right? 2 times of 11, so 2 times 2. So that equals 21 minus 4 equals 17. Therefore, z equals 17, which is good. Look at this bound. And x equals 3y is 21 plus 1 divided by 2. That's from this equation, equation 1. And it equals, that's 63 plus 1, so that's 64. So 64 over 2, that's 32. So x equals 32. Good. The next option is y equals 43. That's when y plus 1 equals 44, 4 times 11. At this time, z equals 43 minus 2 times, and y plus 1 is 4 times 11. Here, 4 times 11, right? So 2 times 4. That equals 43 minus 8 equals 35. So this implies z equals 35. And how about x? X equals 3 times 43 plus 1 divided by 2. So the numerator gives 3 times 43, that's 129, plus 1, that's 130, divided by 2, that equals 65. So x equals 65. Let's continue. Y equals, the next choice is for y plus 1 equals 66. Then y equals 65. That implies z equals what? Z equals 65 minus 2 times, and the multiple is 6, right? 6. 2 times 6. That equals 65 minus 12, which is 53. So z equals 53. And x equals 3 times 65 plus 1 divided by 2. That is what? The numerator is 195 plus 1, 196 divided by 2. That equals 98. So x equals 98. So both values for z and x are within the bound in here, right? X is between 17 and 166. Z is between 9 and 90. So we are good. Let's clean up some space and continue. So the next option is when y plus 1 is 8 times 11. 8 times 11, right? Then y equals 87. That implies z equals what? 87 minus 2 times 8 times 11, right? So that's 8. That equals 87 minus 16, which is 71. So z equals 71. How about x? X equals 3 times 87 plus 1, then divided by 2. That equals what? 3 times 7, that's 21, carries a 2. 3 times 8, that's 24, plus 2, 26, plus 1, divided by 2. So that's 262 divided by 2. So that's 131. Therefore, x equals 131. Are these values good? They are good. They are within the bound. Now, the next option. That is when y plus 1 equals 110. Then what is y? Y is 109. Look at this, 109. Look at this. Then let's check the bound, right? We are almost at the upper bound. So this is definitely the last possible value for y. Therefore, we are almost done. So this implies z equals what? Z equals 109 minus 2 times, and this is for 10 times, right? So 2 times 10. That is 109 minus 20, which is 89. Therefore, z equals 89. How about x? X equals 3 times 109 plus 1 divided by 2. That equals 327 plus 1 divided by 2. That equals 328 divided by 2, which is 164. X equals 164. Are these two quantities good? They are good. They are still within the bound. Let's check the bound here on the left hand side. Good. So these 5 options are all of our solutions for this equation system. That's all of our solutions which satisfy these bounds. Therefore, we have 5 possible values for this n, right? There is one possible value for each of these solutions. To save time, we don't have to solve this n. Therefore, the choice is E, 5. We have 5 possible 3-digit integers that satisfies all these 3 conditions. Good. That's so much for this general approach to solve this problem. As I said, this approach is suitable for almost any values of these, any choices of these, some remainder when divided by some integer. Therefore, I want to introduce these methods first. But that's not the end of the story. I do not recommend these methods in the actual exam. Because look at all these derivations, all of these. Even if you are very familiar with these methods, it'll still take you 15 to 20 minutes to finish everything, right? And this is definitely not doable in the actual exam. Therefore, we have to look at the second approach, which takes advantage of the special choices of these numbers. There are some specialty in them. All right, let's go to the next page and look at the second method. Okay, so let's recall the 3 crucial conditions in this problem. We have a remainder of 2 when divided by 6, right? And we have a remainder of 5 when divided by 9. And we have a remainder of 7 when divided by 11. Good. So this is the remainder, right? And this is the divisor. Good. Are there any specialties or any patterns in these 3 pair of numbers? Probably you have already seen it, but even if you didn't, let's start from scratch. So in such problems, the most difficult part are these remainders. So let's take to the extreme case. What if we don't have any remainders? It's just that this 3-digit number is divisible by 6, 9, and 11. Isn't that simple? That's simple, right? That is the common multiplier of these 3 numbers. Let's write it out. That is the common multiplier of 6, 9, and 11. And how do we find these common multipliers? The most convenient way is to start with this least common multiplier. And to find the least common multiplier, the most convenient tool is to use the prime factorization. Therefore, we can see 6 gives a 2 by 3. 9 gives a 3 by 3, and 11 is a prime number itself. Therefore, the least common multiplier is 2 times, this 2 is from here, right? 3 square, this 3 square is from here. You may wonder, how about this? We removed this, because that's not necessary. We already have 2 3's from 9, so this 3 is redundant, and we will kick it out. And then let's multiply 11. right? This 11 is certainly from here. So this is our least common multiplier of these three numbers. Let's calculate it out. That equals to 18 times 11. So 18 times 11, that is 18, that is 198. Therefore, this number equals 198. So, yay, we are done, right? No, we are not done yet. This is only for the cases that this three-digit number is a multiplier of these three numbers. Or in other words, that n is divisible by 6, 9, and 11. But first, we need to find all possible values. Therefore, it cannot just be this. It has to be n equals 198 times k, right? So are we done this time? No. This is still for the simplified version of the problem. It's not the actual problem. Remember, we still have the remainders. Then how do we deal with these remainders? One thing we do hate is we have different remainders. What if these remainders are not different? They're unified. They're the same. What if that is the case? Let's call that a hypothesis remainder m. Then what would you do if you have a common m as a remainder? Then obviously this n shall equals 198k plus m. Is that right? But unfortunately, these are not unified. They are not the same. Then what now? Now is the time we need to find the specialties that is hidden between these three pairs of numbers. Let's remove these marks so it will look a little bit cleaner. All right, so let's look at the first pair. So when n equals 6x plus 2, what if we give here another 6? That is 6 times x plus 1, another 6. Then what is this quantity? Then this plus 2 becomes minus 4. Is that right? And we can do the same trick with the next two pairs. So n can equals 9y plus 5. But we'll give another 9 here. So this equals 9 times y plus 1 minus 4. Isn't that interesting? This is minus 4. This is minus 4. Let's look at here. So we can do the same trick with this pair. This equals 11z plus 7, which equals 11z plus 1 minus 4. Now, can you see this pattern? Are these remainders the same? They are, right? The same remainder, let's call that m, that equals negative 4. And if you are smart enough, even if without these calculations here, you may still notice that the difference between the two numbers in each pair is 4. So actually, this methodology is fairly common if you know the modulo algebra. And this knowledge is very common, or I should say, this kind of knowledge is required if you are to take the higher level exams like AMC12 or AMC10, or maybe even higher like AME. But anyway, we will not go very deep into that part. We'll just use these very intuitive expressions to show you the motivation behind it. Good. Since we have this common multiplier of minus 4, therefore we can construct our n as 198k minus 4. Therefore, as long as this quantity remains a 3-digit number, that is a viable choice of n. Let's see what values this quantity can take. And we'll do that by varying this variable k. First, let's k equals 1. Can this k equal 0 or negative quantities? No, right? When k is 0 or negative quantities, this n, this will definitely be less than 0. So that's certainly not what we want. Therefore, we'll start k from 1. When k equals 1, n equals 198 minus 4, which is certainly good. That's a 3-digit number, right? And so is true for k equals 2. So we'll keep increasing this k, and then this quantity will get larger and larger until it goes out of bound. Then where is the upper bound? The upper bound is 5. Why 5? Because look at this quantity, 198. That is very close to 200, right? So when that is 200 and the k takes the value of 5, then the first part of this expression gives you 200 times 5, that is 1,000, minus 4, that falls right within our range and near the upper bound. Therefore, the max value that k can take is 5. So how many possible values of n? That is 5. Therefore, let's go up. Let's look at the choice. The question is, how many positive 3-digit integers that satisfy these conditions? The answer is 5. E. E is our choice. If you like this video, please subscribe the channel and thumb up. If you have questions, please comment.